let us discuss a little bit electrical generators. Now, I'm going to start here with a simulation that's available here on that link. I'll run it in a second, but the setup is, this is the principle of a generator. Okay, so we have a north of a magnet, so a U-shaped magnet, and a south. The red is the north, the green is the south, and we have a loop of wire that's placed between the poles of the magnet in the magnetic field. Notice the magnetic field lines here in blue. They go from north to south as we expect. Now that loop is going to be rotated through this crank. In this model, it's going to rotate by itself. In real life, we are going to rotate that through a turbine that's run either through with the kinetic energy of water as it falls in dams, or for example the wind would rotate it in a wind turbine, or it can be due to an engine of some sort, a diesel engine or natural gas engine or steam driven engine in nuclear power plants, etc. Now the ends of that loop, they are connected, one to this disk and the other to the second disk. Now as the loop rotates, the ends of the loop are going to rotate. So to keep the contact, we use brushes. There is one brush on the top and one brush on the bottom. One brush is touching this ring and the other brush is touching this ring. By touching those rings, they keep contact with the loop as the loop is rotated. Okay, let's go to the simulation. So this is the simulation. Okay, pay attention to the generator here. I'm going to run it in 1 second. As we said, this is our loop, and it is connected, the top end here, it is connected to the back ring. The bottom end is connected to the front ring. We have the brushes here. As you will notice, as we start running the simulation, the direction of the current is going to point it through these arrows that you see here. Now the brushes are connected to a resistor, to both ends of a resistor, so we can measure the voltage across the resistor with this voltmeter. Now this graph on top here shows us the voltage as a function of time. It already tells us it's going to look like a sine wave. As the simulation runs, pay attention to what's going to happen to the needle. So I'm going to run it. Again, remember, this is my magnetic field is pointing down, and in this particular case our loop essentially has no flux through it, but it's going to rotate such that the flux is going to increase. Remember, the EMF is minus delta phi over delta t, so if the flux is going to increase, the EMF is going to decrease because of that negative sign. So it's the opposite change, and that's what we will notice here. Okay, you see here the EMF decreasing. It is 0 when I have maximum flux. Now it is increasing again. It is maximum in the negative direction when no flux, decreasing now to 0, maximum flux, etc. You notice the rotation speed. As I increase the rotation speed, the voltage that's induced is going to increase. It's going to increase because in my delta phi over delta t, I have a smaller t now with an increased rotational speed. Smaller delta t results in a bigger EMF. And that's what we are noticing here. Pay attention to the fact the induced current is flipping direction every half a turn of the loop. And that's so one side of the loop is experiencing the flux in one direction. So when it is flipped 180 degrees, then it's a flux in the opposite direction. And that's why we are going to see EMFs in opposite directions. Okay, now in here we have an early version of a generator. You see the same kind of crank here, and in this case we have our coils like this, and we just move the magnets. We are rotating them with the crank, so each of the coils is going to experience either a north or a south. And as the flux changes, of course the current changes, and you notice our voltmeter here again is flipping back and forth in both directions. Actually, sorry, here, if we undo this, it's flipping in both directions. Now, going back to the original one, so this is why we call it an alternating current, because it looks like a sine function, and because the direction of flow of the current changes twice every period. I mean, because the direction of the current changes from positive to negative and vice versa. Now, especially early on, when people started implementing electricity, they wanted to have DC power supplies, not direct current power supplies that have a constant polarity, not a polarity that's changing like this. To do that, they had to design a way for doing it. So if we look here, the way they did it, the crank, as it rotates, so actually had a mechanical switch here. So for half a turn, the wires are connected one way. For the other half a turn, you swap them. Okay, the image does not show it very well, but the idea is every half a turn you swap the switches. And you notice here, then our meter is flipping only in one direction. So we have a direct current. It's not a constant current, but it is always in the same direction. A more modern alternative to that is through what we have in here. So actually in here, instead of connecting the loop to two rings, what we do, we connect it to a cylinder that's cut in two. One half is connected to one end, and the other half is connected to the other end. And these two halves are insulated. What we see here in black is an insulation between both parts of the cylinder. And then we have the brushes before, like before. So what's happening here, the brush is touching one end of the loop during half a rotation, and the other end during the other half of the rotation. So instead of having the mechanical swapping, we have it happening here by the brush actually touching one end or the other one. And you notice here the meter is again moving only in one direction, but look at the voltage here. You notice the voltage in this case is all the time positive. It is not constant, but it is positive. Notice here, if we rotate the coil in the opposite direction, then of course we are going to have an EMF in the opposite direction. It's all the time negative, but it's again in the same direction. So it's again direct current that we are generating, as opposed to alternating meaning changing sign every period.